Processing modern artificial intelligence models requires calculating billions of parameters in a single instant, a staggering computational task. A traditional central processing unit handles workload by dividing tasks across time, moving data through a sequential gateway, one instruction at a time. This serial processing created a fatal choke point, effectively trapping theoretical AI in the lab for decades. The math for a digital brain existed, but humanity lacked the physical engine to run it. That changed in the late 1990s, driven by an explosion in consumer demand for realistic, three-dimensional video games. NVIDIA's GeForce 256 arrived as a specialized solution to offload geometry calculations from the CPU. This flyer highlights its 256-bit 3D processor and 50 gigaflops of dedicated floating point capability. Its power came from parallel processing. Instead of dividing tasks across time, it divides them across space, calculating the lighting and geometry of millions of pixels simultaneously. The gaming industry had inadvertently funded the creation of massive parallel supercomputers distributed to the public as consumer entertainment devices. In 2006, NVIDIA released CUDA, a platform that allowed researchers to program these graphics chips for non-graphical, general-purpose calculations. By 2012, Geoffrey Hinton and his team at the University of Toronto were leveraging that access to solve massive visual recognition problems. This split-screen diagram shows the overlap. On the left, a game character is rendered using matrix multiplication. On the right, a neural network calculates its weights. The underlying math is identical. Researcher Alex Krzyzewski utilized this overlap to run a 60 million parameter neural network across two consumer gaming GPUs, bypassing their memory limits by splitting the model between them. Their model, AlexNet, won the 2012 ImageNet competition with an error rate 10% lower than the closest competitor. That victory demonstrated to the scientific community that the graphics card was the physical engine AI researchers had been waiting for. After the AlexNet breakthrough, hardware manufacturers began altering their silicon to prioritize AI workloads over traditional graphics rendering. In 2017, the Tensor Core was introduced for matrix math, executing massive calculation clusters in a single cycle. It gains speed by dropping unnecessary decimal points. Neural networks tolerate this lower precision, allowing training data to flow exponentially faster. The GPU was no longer just a tool for simulating virtual worlds. It had been re-engineered to interpret the real one. Modern GPUs have evolved into the interconnected foundations of global data systems, moving far beyond the confines of individual desktop computers. This server array houses the NVIDIA Blackwell architecture. Each GPU here packs 208 billion transistors and utilizes a 10 terabyte per second chip-to-chip interconnect. The pursuit of better shadows and polygons in video games inadvertently funded and forged the physical architecture that now runs the world's most complex neural networks.